Hi everyone. So for this video, it's just going to be a quick overview of solubility equilibrium. So we can get started. As you guys probably know already, a KSP is the solubility product constant, and this means that it denotes the degree in which a compound dissolves in water. So as a general rule, if we increase KSP, so this value, it is equal to an increase in the solubility. So something that dissolves in water completely would have a very large KSP, whereas something that does not dissolve as much would have a very small KSP. As a general equation, maybe we have a salt XY2, and that's a solid, and it dissolves into its ions. And in that case, our KSP equation can be created from this, and it's just going to be the concentrations of its products. So the concentration of X multiplied by the concentration of Y, but this one, of course, is going to be raised to the second power because of the two coefficients. Additionally, the reactants are not going to be present in this equation because it's a solid, so it would just be denoted as 1. So I have 3 practice problems. The solubility of PbBr2 is this many grams per this for a solution. Determine the value of the solubility product constant for this strong electrolyte. So in this case, we should probably just start by first writing out the equation. So Pb and it dissolves into its ions. And we can denote what it dissolves into by using an X. And this X is equal to the molar solubility. So this would have to be 2X because it's 2 times the moles that it dissolves into. So in order to find the KSP, we can use the KSP equation. KSP equation would be the concentrations of the products, which in this case, when we substitute for X, would look something like this. So X, 2X squared. And then we can simplify this further by making it 4x to the third. In this case, we're still looking for X, but what we're given is our molar solubility, so we can use that. Our molar solubility needs to be in moles, though, molar, so that's moles over liters. So in order to do that, we have to convert what we are given as our initial. So we have 2.427 grams over our liters. We can multiply this by our molar mass. This is the molar mass of lead, bromide. For 1 mole. And we get 0.0116 molar. So we can plug in this value for X. So KSP and then this is to the third power. From there, we can get our KSP, which would be 6 times 3, 6.3 times 10 to the negative 6. Okay. So for our next question, we have application question. So along icicle-like formations that hang from ceilings and caves, right? They're formed from calcium carbonate. These droplets are saturated with calcium carbonate and they hang and evaporate, leaving solid calcium carbonate behind. The KSP is 4.5 times 10 to the negative 9. What is the volume of water droplets saturated with calcium carbonate that could be required to form a small stalactite that has a mass of 1.0 kilograms? So I guess we would start again by making our equation. So we have calcium carbonate, CaCO3, dissociating into calcium plus carbonate. And in this case, we would both just have X and X as our molar solubility. So our KSP equation would look like X squared, and this would be equal to 4.5 times 10 to the negative 9th. In this case, we have to solve for X in order to find out how much volume that we would need for a mass of 1 kg. So X in this case would be equal to 6.7 times 10 to the negative 5th. All I did was take the square root of the KSP. And from here, we can convert to find out how many liters we need. So we have our kilograms. Remember, we are converting kilograms to grams first. And then we can use the molar mass as a conversion factor. So 100 grams CaCO3, this is its molar mass, over 1 mole. And then we can use our molarity as our conversion factor. So 6.7 times 10 to the negative 5th moles over 1 liter. This way we can find out how many liters that we need. And in this case, after everything crosses out, we have 1.5 times 10 to the 5th, not negative. This is a large amount, so it's 1.5 times 10 to the 5th. For our next question, what is the solubility of barium sulfate in a solution also containing 0.05 molar sodium sulfate, which is fully soluble? So the KSP value for barium sulfate is 1.1 times 10 to the negative 10. So they're giving us the KSP value, so we should use this, this compound in order to make our equation. So we're going to use EaSO4 as our equilibrium. So it dissociates into its ions. So 4, 2 minus. And these are going to be X for its molar solubility. But as we can see, we also have sodium sulfite, which is fully dissolved, and it fully dissolves into sodium ions and sulfate ions, as you would expect. So this amount right here can be added to our X on this side, because this is also the initial amount that is in solution. In this case, our KSP would look a little different. So we have X and X plus 0.050, and that'll be equal to 1.1 times 10 to the negative 10. In this case, our KSP is small enough that we can disregard this X for the sulfate, because the amount of molar sulfate that we already have is large enough that the X does not alter its amount significantly. So this turns into X is equal to 1.1 times 10 to negative 10. And in this case, we get that X is equal to 2.2 times 10 to the negative 9. And this value of X would be the molar solubility of barium sulfate. So this is our answer. All right. So thank you guys for watching. I hope you learned something new, and good luck studying.